in this case, we got the set of 2 by 2 matrices of this form that are basically diagonal matrices. And the sum and scalar multiplication is defined the usual way. That means if I pick the two elements of the set M and I sum them up, I obtain this. Just sum element by element of the matrices, and we obtain this. And from here, it's important because here we can check that what we obtain is again a diagonal matrix. That means that the operation is closed. So this part here actually proves the first axiom of vector spaces. And the scalar multiplication is defined in the same manner. It's just multiplication by each of the elements of the matrix. And we obtain again a diagonal matrix. Again, this is still in the set M, so the multiplication by a scalar is closed. So the sixth axiom is proved. So based on this, we got this set, we got these two operations. We need to check if this, we need to verify if it is a vector space. So let's start. The first axiom was already proved. It's just the closeness of the summation operation. And the sixth axiom was also proved. It's just the closed of the scalar multiplication. So in this case, we need to prove the commutativity of the sum operation. So u plus b, this is just a1, 0, 0, b1 plus a2, 0, 0, b2. And this result we already know what it is from the previous slide. So it's just a1, a2, 0, 0, b1 plus b2. Great. And the right-hand side of this equation is v plus u. That means a2, 0, 0, b2 plus a1, 0, 0, b1. And what happened here is that we obtain a2 plus a1, 0, 0, b2 plus b1. But these elements here are just real numbers, so they commute. And this becomes a1 plus a2, 0, 0, b1 plus b2. That means that these both expressions are the same, so checked. The second axiom is satisfied. The next, here we need to define an extra vector, that is the vector w, is a3, b3, still diagonal matrix on M. And we need to prove the associativity property. That means u plus v plus w, that's going to be a1, 0, 0, b1 plus here. And the sum of these two matrices will be a2 plus a3, 0, 0, b2 plus b3. And then we need to sum these two matrices here. And what we obtain is a1 plus a2 plus a3, 0, 0, b1 plus b2 plus b3. And then the right-hand side of this expression reads as a1 plus a2, 0, 0, b1 plus b2 plus a3, b3. And this sum is equal to a1 plus a2 plus a3, 0, 0, b1 plus b2 plus b3. And these two matrices are the same, so the third axiom is satisfied on this space. Next, we need to define the zero vector. That means the ones that satisfy this property. If we pick some arbitrary vector on the space and we sum with zero vector, we obtain the same vector. And this part is just an addition of the commutativity property of the sum operation, but it's enough to prove just one part of it. That means u plus the zero vector returns the same vector. So the zero vector in this case is defined as the zero matrix. And you can observe that it's still diagonal matrix. It's not diagonal in the strict sense, but it satisfies the property that is required. So this is part of this set. And then we pick u plus the zero vector. In this case is a1, 0, 0, b1 plus 0, 0, 0, 0. And this returns the same vector, a1, 0, 0, b1, that is just u. So this axiom is satisfied. The next is to find the inverse of a vector in this space. I know that they are matrices, but in this case we're determining if it satisfies the axioms of a vector space. So that means that these elements are going to be vectors, even though that they are matrices. It's just a matter of vocabulary. So for any vector u on this space, we can define the inverse of that vector such that when we sum them up, we obtain the zero vector. That means that we can define here minus u as minus a1, 0, 0, minus b1, such that when we sum with the original vector u plus minus u, what we have is a1, 0, 0, b1 plus minus a1, 0, 0, minus b1. And this, after sum this, we obtain a1 minus a1, 0, 0, b1 minus b1. And this returns us just the zero vector. That is the zero matrix in this case. So this is the way to define the inverse in this space, and even more, it is still diagonal. So it is still a diagonal matrix, so it satisfies the condition to be part of M. That means that minus u lives in the space M, and therefore the fifth axiom is also satisfied for the space M. Then we got this property for the scalar multiplication. The axiom number 6 was proved at the beginning when we checked that ku is still part of the space. So let's see. The scalar multiplication is defined in the usual way. That means that we multiply this scalar, or just a real number, by each of the elements of the vector. In this case, is a matrix. So let's see what happened with the left-hand side of the expression. K plus M will be just another scalar, and U will be the matrix. So we got K plus M, and here the diagonal matrix. And after multiplying, we have here K plus M, A1, 0, 0, and here K plus M, B1. Then what happened here is that these elements here, all these elements are real numbers. That means that they satisfy the distributivity property. So we can distribute a1 to each of these elements inside of the parentheses. So we obtain here k a1 plus m a1, 0, 0, k b1 plus m b1. And look, this is the same as the summation of two matrices. So we can separate by the sum in the sum of two diagonal matrices. That means Ka1, 0, 0, Kb1 plus M A1, 0, 0, and MB1. But this is just K u plus mu. Therefore, this axiom is satisfied as well. The next is another kind of distributivity property with respect to the scalar product. So let's see what happened with the left-hand side. So k times u plus b. We know already what is the summation of these two vectors. So we got k times the diagonal matrix a1 plus a2, 0, b1 plus b2. And then we multiply k by each of the elements of this matrix, and we got k a1 plus a2, 0, 0, k b1 plus b2. Then what happened is that each of these elements are real numbers, so we can distribute k along the elements on the parentheses. So we got here ka1 plus ka2, 0, 0, kb1 plus kb2. And here we can separate again, just as we did in the previous example, the previous part. And we got ka1, 0, 0, kb1 plus ka2, 0, 0, kb2. And here you can observe this is just ku plus kv. So yes, the eighth axiom is satisfied. We need to check now the ninth. We are almost ending this. It's quite long to prove that a vector space is a vector space, but we need to check each of the axioms to say that a vector space is a vector space. So here we need to prove a kind of associativity property related with the scalar product. So we got k times mu. This equals to k m a1, 0, 0, m a2, and then we multiply k to this matrix, and we got k m1, 0, 0, k m a2. Then km is just an scalar, so we are multiplying one scalar to the whole vector u. In this case, that is equals to having km a1, 0, 0, km a2. And you can see both of these matrices are the same. That means that this axiom is also true. And the last but not less important is, and actually is quite trivial, is the identity for the scalar product. So the identity in this case is just the number 1. So 1 times the matrix a1, 0, 0, b1, it returns just the same matrix as is expected. So yes. So we have checked that each of the 10 axioms of the vector space are satisfied for this space M. That means that M is a vector space.